Hi guys, in this lecture video, I will be discussing the halogenation reaction of alkenes with you. So this is a type of addition reaction where two halogen atoms are being added across the carbon-carbon double bond in an alkene. And here is the scheme of a halogenation reaction. So you'll be taking an alkene, reacting it with a halogens. And so the halogen can either be the bromine or the chlorine. So these are the two most common types of halogens. So we will not be able to do this with iodine because that will react too slow, and with not the fluorine either. But most commonly will be the bromine or the chlorine. And here in the presence of CHCl3, which is basically the chloroform as the solvent. And the product of this reaction is when we will have two halogen that we added to this two carbon-carbon double bond. So we end up with one chlorine on this carbon and the other chlorine on this carbon right here. And again, this used to be the double bond between these two carbon. So overall, this is a halogenation reaction of alkene. And please note that these types of reaction right here are basically different than radical halogenation reaction. Because in radical halogenation reaction, it's the reaction condition would be different, in which that we have light or heat or a types of radical initiator in that types of reaction. But here, this is a completely different types of reaction. It does not go through the radical reaction mechanism. Okay. And now, let's now talk about the stereochemical outcomes of this halogenation reaction. Then what we have observed is that for most simple alkene, the halogenation reaction appears to proceed through a process that we call the anti-addition. And this is what affects the stereochemical outcomes of the products. What this anti-addition right here means is that when the two halogen are added to the carbon-carbon double bond, they are then added to the opposite side across those two carbon. So for an example, when we take this cyclohexene right here and doing a bromination on it, and so the two bromine will be added to this carbon-carbon double bond. And now as for the stereochemical outcome, one bromine will be pointing up and the other bromine will be pointing down. So we will be forming one of the product where this will be the stereochemical outcome. We will also be producing the other enantiomer, where now the bromine on this carbon one right here would be pointing down, and on the other carbon it is pointing up. So in this case right here, we can see that these two molecules right here, they are enantiomer, and both of them get produced. So what we have right now would be a racemic mixture of these two products. So that the stereochemical outcome in the halogenation reaction of alkene. They proceed through the anti-addition reaction. And again, anti-addition means that the two halogen are being added on the opposite side of the double bond. And that would what dictate the stereochemical outcome. And now let's talk about the reagent a little bit. And as I mentioned before already, this does not go through the radical reaction mechanism. But now let's take a look at the reagent. So we can see that the bond between the two halogen, it is a non-polar bond. However, it is polarizable, meaning that between two of this halogen right here, one of the halogen will be able to basically pull the electron from the other halogen, and they go back and forth. But the electron not reshaped equally between these two atoms right here. Even though it's non-polar, but it becomes polarizable, meaning sometimes electron can be shifted to this bromine and the other time on the other bromine. And the consequence is that one of the bromine end up being partially negative and the other bromine end up being partially positive. And that's the interesting part about this reagent right here. Now, because one of the bromine can become partially positive, therefore that bromine become electrophilic right there, and therefore it is a good electrophile. So if we were to have something that can serve as a nucleophile, in our case in this reaction, that would then be the alkene. So the alkene can serve as the nucleophile and come in and attack the electrophilic bromine in one of this bromine right here. So that's what happened in the course of a chemical reaction. And now, so here is the mechanism of this, how this reagent would interact with our alkene. So our alkene, again, it can be a good, it can be an okay. So this is basically a weak nucleophile. So it will be able to come in and attack one of this bromine, that is positive, and then that will then kick off the other bromine right there. Now, so in this reaction mechanism, we combine two steps together, but if we were to actually draw out the intermediate form in here, then we will see the following. We'll be forming this product right here, where we will now have the bromine, and this carbon right here will become a carbocation, and the other bromine have broken up already and becoming negative. So that's what we have right here. Now, the reason why we don't draw this intermediate, because it is highly unstable. It doesn't even exist at all. The reason is because the minute that we form this already, this bromine right here still have a lone pair of electrons. So that's why that it can behave as a nucleophile, and that will then come in and attack this carbocation right here immediately. So in the end, what we get in right now will then be this 3 membrane. So the membrane where the bromine is positive in it. So that is what proceed, and that's what we have. And this is then referred to as the bromonium ion. And once we have formed this bromonium ion already, and we still have another bromide that have fallen off from the reagent that floating around in solution. And we know that this is a nucleophilic reagent, right? And so that will then come in and attack this 3 membrane right here, because this 3 membrane or this bromonium ion right here is not really that stable, right? Imagine you have a 3 membrane, and now the bromine is also positive as well. So that basically still a lot of the electron from these 2 carbon right here. So this ring is ready to be broken, okay? And in fact, it is ready to be broken even before the other bromine come in to attack it. So in the next step, then now the other bromine come in to attack. In order, and so, and here is the part that make it interesting and explain why did this reaction right here proceed through the anti-addition. As another bromine come in to attack, it come in either attack this carbon or this carbon right here. So in this case, we're choosing this carbon, and it have to attack this carbon right here from the back side of this CBr bond right here. And this is very similar to the nucleophilic attack in an SN2 reaction. So this attack from the bottom, the opposite side. And that is the explanation why that in the product they've been formed, this bromine is added to the bottom. So again, this is the carbon-carbon double bond right here that it used to be. And now the bromine here is being added to this side on the bottom. The other bromine that was already on this would now be on top. So in the end, we have 2 bromine, one is on top, the other one is on the bottom. And that is the anti-addition reaction right there. So that's the explanation why the 2 bromine are added on the opposite side. It is dictated by this nucleophilic attack right here, where the bromine has to attack from the opposite side. And now, so that is what we would have when we have a simple alkene. What happens if we don't have a simple alkene? And an alkene that is not simple would be one that have different substitution on it. So here in this case right here, we can see these 2 alkene carbon right here are equally substituted. So the question will be, what happens if these 2 alkene right here are not equally substituted? Let's say we were to have a methyl group on this carbon, and now this one doesn't have anything, there's a hydrogen on it. So what would happen then? Then the answer is as follows. If we were to have that types of alkene right here, then here in this case, this will have a methyl group on it. Okay, and now it does play an important role, because if we were to have this alkene right here on the nucleophilic attack, this is when the bromine would then come in and attack the more substituted carbon. Okay, please remember that. Okay, and the reason why that the bromine will come in and attack the more substituted carbon is because this ring right here, it actually almost, it kind of partially broken already before the nucleophile even come into attack. And because the more electron-rich carbon, so the more substituted carbon is more electron-rich, so that have more electron to donate to this ring right here. So therefore, the partial part of charge on the most substituted carbon is bigger compared to this other carbon that are less substituted. So this most substituted carbon is a better electrophile. So therefore, the bromine will then come in and attack this carbon if this carbon right here is more substituted. Okay, so that is the factor that can also affect the regioselectivity, because about where did the bromine come into attack when we have this bromonium ion. And again, if we have a complex alkene, then these two carbon right here would not be equally substituted. So please remember that it will attack the more substituted carbon. So more substituted carbon is being attacked by the other bromine. So that's the reaction mechanism of this, and that's why it explains the anti-addition product that we have observed in this halogenation reaction. And overall, the configuration of the starting alkene really must dictate the outcomes of the product in terms of what kind of stereochemical outcome that we will be getting. For an example, we would have this alkene right here where we have a cis alkene. When we do this halogenation bromination reaction on it, then now we will be having the product where again the two bromine, one will be pointing up, the other one will be pointing down. And the other enantiomer, where now this is pointing down and this is pointing up. And again, these two molecules right here, they are enantiomer. And if we were to now have a trans alkene and we do this bromination reaction on it, then now we'll be getting this again. This bromine is pointing up, and this one is pointing down, and the other product with this one is pointing down, and this is pointing up. And the stereochemical outcome of these two products right here is again, they are enantiomer of each other. And now let's try some of this example right here. So in the example number 19, so if we were to react this alkene with bromine, then what will happen? Then so again, we see that this would undergo the halogenation reaction where the two bromine will be added across this carbon-carbon double bond. And now the two bromine will be added to the opposite side of this double bond. So if one point up, the other one will be pointing down. So in this case right here, the product that we were producing will be as follows. So we can have a bromine point up here, and the other bromine that is pointing down here. And if this is point up, that means the methyl group here have to be pointing down. And if this bromine is pointing down, then that means the methyl group here will then be pointed up. So that will be the structure of the products. And we will also be producing the other enantiomer of these products as well. Okay. And now let's try this example number 22 right here, because this is an example of when we do not have a simple alkene, but this is quite a complex alkene right here, in which this molecule right here is a chiral molecule. And again, this is chiral because there is a chiral center in here. So let's now talk about this reaction right here. Anytime we have a chiral starting alkene, then this is when we will be getting selectivity for one of the enantiomer over the other. So therefore, we will not be getting an equal racemic mixture of the two enantiomers. Okay, so please keep that in mind. And now let's figure out what will be the major product here in this reaction. So when we have this reagent right here, then you can see that, so here is our cyclohexene, and now this isopropyl group is pointing up. So that means this top face right here, or this up face of this, is more bulky compared to the bottom face. So therefore, as it come in to interact with the reagent, the bromine will be approaching this reagent right here from the bottom side, because the bottom side less steric compared to the top side. So what we'll be getting is as follows. If we were to draw out the reaction mechanism, the intermediate, this is something that we'll be getting right here, where now the bromine or the bromonium ion is being produced where the bromine approaches from the back. So that's what we will have right here. And now followed by the nucleophilic attack by the other bromine. And here in this case right here, because again, that these two carbon right here, they're equally substituted. But however, sterically speaking, they're not the same thing. This carbon right here in next to an isopropyl group compared to this carbon. So in terms of steric hindrance, they are not equally the same. So will that play any role at all? Then the answer, yes, it may. Because when the other bromide come into attack, the other bromide have to come in attack from the top, right? From the top, because again, they have to attack in the opposite direction from this carbon and bromine bond right here. So in this case, they have to attack from the top face. And now on the top face, this isopropyl group right here would create the steric hindrance. So therefore, the bromine would then be able to come in and attack this carbon right here, the other carbon, because that is further away from the isopropyl group. So again, this would then allow us to have some sort of selectivity. So therefore, the major product here in this reaction right here will then be as follows. So now we have a bromine attacking from the top. So this bromine will be pointing up, and the other bromine will remain to be on the bottom. And then this would then be our major product right here. We do not produce an equal mixture of the other enantiomer, but here in this case, this would be the major product of this reaction. So again, the complexity and the substitution on this started alkene kind of dictates what kind of products that we'll be getting. Are we getting a racemic mixture, or are there any selectivity at all? Then again, that is being answered by the structure of our started alkene.